already visited it, correct?
Yes,
Is that
yes,
what you're checking?
yes, we have already visited A, right? However, if A was, let's say, 6, and then B was, as usual, 4, would we have explored A first? The reason we are not exploring A again in this particular graph here is because we explored B first and then A. However, if A was 6, would we have explored A first or B first?
B.
B, right? So we get B equals to 4, we are done. And now that we have explored B, we would explore other vertices to from going from B, and that what gets us A equals to 2, that is 4 minus 2. So even if we have looked at a vertex A that has a value of 6, we are not popping it from the queue because we are always going to explore it with the shortest distance. And since we have found a lower distance to A, we are guaranteed to look at this particular distance rather than A equals to 6. Do you agree?
Yep.
Yes, exactly. So if we have a distance that is longer, we are always going to find a distance to A that is shorter. That is the priority queue thing. However, there are cases where this does not apply, and this is one of those cases here. So if A is a distance 3, B is a distance 4, we are going to explore A first. And if we have already explored A, we are not going to revisit A because we have discovered it. And that is the reason Dijkstra does not work with negative edges.
Yeah, I think I was getting hung up on where you would when you would update. And I think one example would be if S to B was like 1 and
Mhm,
then B to A was 3, you'd
mhm.
obviously explore B first,
Yes,
right?
and that works.
And
And
then,
that
yeah,
works.
right, exactly. That would be an example of where you would update when
Exactly.
you go from directly from S to A. You would say, oh, that only costs 3 versus going S to B, which is 1, and then B to A, which is like
Ex
another 3, which is 4. So you would then
exactly.
say S is the parent node, and it only costs 3 to go directly from S to A.
Exactly. So if that is the case, if you think about it, what you are saying is as long as we follow this discovery route along the true tree that we were to explore in the first place, we are fine, right?
Right.
It,
Yeah, I was just getting a little hung up because I was trying to think of an example where you would have already discovered A, but then you'd come back and update. Uh,
yes, because A was discovered first, and that was not part of the ideal situation where we needed to explore B first, right?
right.
Right. So what you're saying is we always need to explore B first, and that was the reasoning behind this particular graph here, where we are saying that if we had a singular set of vertices in a graph, then negative edges does not matter because that is the shortest path anyway. If that is the case, or if it is the case that we are always exploring the vertices along the shortest distance vertices in the first place, if let's say there is some divine oracle there and that tells us which vertex to explore next, then that works out. However, there are cases, as we saw here, where that might not be true, and in such cases we might not get the shortest distance using Dijkstra. Does that mean? Because in this particular scenario, we are always going to explore A first. If there was a scenario, as you say, that A had a distance of some other thing, B had a distance of, let's say, -1, in that scenario, B would be explored first and everything is hunky-dory. There is no issue. The reason is we need to explore B first, and that might not always be the case.
Right.
Right? And in order to fix that, what we need to do is uh, we need to be able to update A again, right? Even if A had a distance of 3, we need to be able to update 3 again. And in that particular scenario, it requires more time complexity, but it allows us the capability of using negative edges. So we'll yes, that was, I was thinking of an example, but that was a bad example, but essentially for the network and routing and switching case, let's say that we figured out a case where we have a routing network that uses, I don't know, what's that thing? Quantum pairing or something, where you do not take any time and you go backwards in time, like Back to the Future kind of stuff, and it takes less time than actually going there. In that particular scenario, you might have negative edges, and negative edges might be a thing in other scenarios as well. And Dijkstra might not be is not the best algorithm in order for those particular problems, because in order for Dijkstra to work, as you say, we need to always follow the best possible path, and then it would give us the best possible answer. However, that might not always be the case for random other graphs. So for that, we would look at this particular algorithm, that is Bellman-Ford, that essentially has a nested loop that repeats v-1 times and repeats for all edges, not just the edges connected to us, but repeats for all edges, and updates all edges and all vertices every iteration all the time for v-1 iterations, right? So does everyone understand this particular scenario, that in order for us to figure out a way to work with negative edges, we need to be able to update vertices that we have already visited before? Because we can somehow find a vertex or a path connecting to this vertex that can have a negative edge and that can actually reduce the distance that we have already seen. That is not an issue with all positive edge distances, but if we have a negative distance, it might not always work. So does that make sense to everyone? The difference between Dijkstra and Bellman-Ford, and why one works and the other does not. Nobody else?
Because is that because you're basically traversing the graph in every possible conceivable way?
Yes, essentially, yes. It is not.
Whereas Dijkstra has a very specific way of traversing the graph where you're always going towards that minimum. You're always picking the node on the minimum path. Kind of like a brute force versus a
No. Okay,
right.
so no, let me just explain this a bit. So let's say that we have this particular graph, right? So S goes to A with a distance of 3, and I'm just basically writing down this particular graph, right? So S goes to B with a distance 4, and B goes to A with a distance of -2. Right, so this is one graph, and let's say that this entire, I'm just going to copy this graph as another graph, and let's say that B has a distance of, as you said, -1. Okay, so let's say that for this first graph, I am going to explore starting from S. So for that, I start off from S, and I basically look at all the vertices that I have seen from S and add that to my particular queue or my priority queue. So I have seen A and B, right? So I basically add from S, I get a distance of A to 3. From S, I get a distance of B for 4, right? The same scenario for this one. Let's just apply Dijkstra here as well. And from S, I again see A and B. And from S to A, I get a distance of 3. And from S to B, I get a distance for -1, right? And since it's a priority queue, this gets automatically sorted to B equals to -1 gets there first, and then we have A is 3. And then we have A equals to 3 and B equals to 4 for this particular graph here, right? So up to now, is everyone clear up to here? So this is what the priority queue would look like. So if this is my priority queue, this is what it would look like so far.
Right.
For both of these vertices. Right? Any confusion so far? Okay. Now, if this is my priority queue, then what is the next vertex that I'm going to choose in this scenario? B is -1. And once I explore B is -1, I'm going to expand B and I'm going to find A that will now get the distance of -3, right? So I am going to choose B is -1 here. So B with a value of -1. And then I'm going to expand from B to get a new value to A. And A has a value of -2. So -1 plus -2, I get a value of A with a value of -3. Now, I am allowed to add this particular vertex to my priority queue because A has not been explored yet. A is in the priority queue, but we have not explored A yet, right? Now, in this scenario, in this particular graph here, we are going to explore A with a value of 3. And from A, we do not have any other vertices anywhere. So we remove this, but that doesn't really matter. But the next thing that we are going to explore is B equals to 4. Right, so the next thing that we are going to explore is B equals to 4. So we get a value of B is 4. And then we expand B. Expanding B gets us this particular value. A is -2 from this original graph here. Now, can we insert this particular vertex to this priority queue? Yes or no?
To insert something in the priority queue, you check that that node has not yet been visited, correct?
Exactly. So we
So if
cannot,
you're asking if node hasn't been visited, add to
then we
priority
insert.
queue.
Then we
Okay.
insert. Exactly. But can we insert this A equals to -3 to this particular priority queue?
Yes, because it hasn't, A has not been visited
A
yet.
has not been visited. And since it's a priority queue, this value of A goes above and we get a value of A equals to -3. We pop out A and we get a value of -3. This is fine. And if we are following the correct route, remember both of these algorithms are Dijkstra algorithms with negative weights. So if we are following the correct, so to speak, correct route, in that scenario, the route is S to B and B to A. Then this works and we have the correct tree. However, there are cases where we cannot add a particular vertex because we have already expanded it. And that is the downfall of Dijkstra, and that is the reason we cannot have negative weights, because Dijkstra assumes that once we have explored a particular vertex, that is expanding and all of those things are done, we have already found the shortest distance altogether. We do not need to add it to the priority queue anymore. And why is that assumption there? Because Dijkstra assumes that all of those vertices are positive vertices or zero weight vertices. And if we are going through in that sorted order, we are always going to find a vertex that has the shortest length and we are going to add that to our list. However, if we have negative vertices, that does not work out. Does that clear things up?
Yes, I think the example that I was getting hung up on is if S to B was +1 and